Part 2 of Section 5.2, Triangle Midsegments and Angle Bisectors. We finished Part 1 with Example 3. Now we're on Example 4. Environmental Science. A geologist wants to determine the distance of AB across a sinkhole. Choosing a point E outside the sinkhole, here's the sinkhole, here's point E. She finds the distances of AE here on this side of the sinkhole over to here, and the distance of BE, the other side of the sinkhole, to the same point E. She locates the midpoints of C and D of segment AE. So she figures out the midpoint here, and she figures out the midpoint of EB, which is D. And she comes up with the midsegment, or one of the midsegments. And then she measures CD. She measures across here. She comes up with 46 feet. She's trying to find the length across the sinkhole right here. What is the distance across the sinkhole? So we've got a triangle and we've got one of its midsegments. If we use the midsegment theorem for triangles, then we can use this midsegment, the second part of the theorem, to say that this is half the length of the third side. In this case, the third side is the length across the sinkhole. So by the midsegment theorem, the second part of it, we can state that CD, the length of CD, is equal to half the length of the third side we need, AB. Substituting in what she found when she measured across from C to D, 46. Placing that in the equation, that equals half the length of AB. Solving that equation, multiply both sides by 2. On the right side, we get just the length of AB. On the left side, 46 times 2 is 92. Therefore, the sinkhole is 92 feet across. Example 5. Determine the length of segment BC, or simply find the length of BC. Which theorem did you use to find the length? Okay, here we have, if you'll notice, there are two triangles within one big triangle. However, take a look, we have a perpendicular bisector here. BD is a perpendicular bisector of AC. We know that because there's a right angle symbol here and a tick mark here and here. That configuration implies a perpendicular bisector. So this is the perpendicular bisector, and using one of the theorems that we learned, perpendicular bisector theorem, states that if a point is on the perpendicular bisector of a segment, then it's equidistant from the endpoints of the segment. Here's the segment that's being bisected. Here are the endpoints, A and C. Any point along this perpendicular bisector is equidistant to both these 2 points. For instance, this point right here on the perpendicular bisector is equidistant to A as it is to C. In other words, this length and this length are the same. In this particular example, B is the point we're interested in on the perpendicular bisector. So, by the perpendicular bisector theorem, we know that BA is equal to BC. It's equidistant to both those endpoints. So we state that by the perpendicular bisector theorem, the length BA is equal to the length of BC. We have an expression for the length of BA, which is 4x. So substitute that in. Equals the length of BC. Just plug that in. Ultimately, we're going to find the length of BC. First, we need to find x. Take the equation and solve for x. First, subtract 4x from both sides. 4x minus 4x is 0x, or just 0, equals 6x minus 4x is 2x minus 10. Get x by itself by adding 10 to both sides. We get 10 over here. 0 plus 10 is 10, equals 2x. Divide both sides by 2, and x is 5. So since x is 5, we can now find the length of BC, which was 6x minus 10. Substituting in for x, we have 6 times 5 minus 10, which is 30 minus 10, which is 20. So the length of BC is 20. Example 6. In example 6, a park director wants to build a t-shirt stand at point T. And this point T is equidistant from the roller coaster ride, which is here at R, and the spaceship chute ride, right over here at S. Use a compass to determine the possible locations of the stand, the t-shirt stand. Pick a location and then indicate the distance from stand to each ride. Okay, so if we need this new t-shirt stand to be the same distance from itself to the roller coaster ride as to the spaceship chute, there's not just one place that could be. If we draw a line segment between the spaceship chute ride and the roller coaster ride, that can be our segment that we can bisect. So, recalling how to construct a perpendicular bisector from earlier this semester, we use these two endpoints, and we want a perpendicular bisector, and anywhere along that perpendicular bisector will give us any location for a t-shirt stand that we want. So, take your compass. I'm going to start at putting my point at point S. Pointing my compass on S. Make sure that the compass is set a little bit more than half the distance between the R and S. Draw an arc below and above the segment. Keep the setting on your compass. Bring your point of your compass over onto R and draw two arcs, one above through the first arc and one below through the first arc, like that. Take your straight edge, connect those two intersection points for both arcs very carefully, and lightly draw a line or dashed line. I'm going to use a dashed line. This is the perpendicular bisector between R and S. So, what does that mean? That means the t-shirt stand can be any point along this line because it's anywhere on the perpendicular bisector. So, we're using the perpendicular bisector theorem. Let's say we want to put T here, our t-shirt stand. We're going to indicate it's the same distance to the coaster ride as it is to the spaceship ride. So I'll use two tick marks here and two tick marks there. On the other hand, maybe they want it to be here. The t-shirt stand way down here. It's still equidistant both to R and S. So, and I'll indicate that by doing this one more time. from T to R and from T to S. TS is congruent to TR. The distances are the same, in other words. And I could create many more points. I could put T anywhere as long as it's along that. So, TR is equal to SR. Any point along the perpendicular bisector. Example 7. Find the length of segment RP. Segment RP right here. They give us 2x plus 25. State the theorem you used to find it. Here we have an angle bisector. We know that NR is an angle bisector because these two angles that it produced are congruent. So NR is angle bisector of angle LNQ. If we use the perpendicular bisector theorem, we can take any point along this line and it will be the same, it will be equidistant to each one of these rays in the angle. So this point right here, according to the theorem, is equidistant to M. Remember, equidistant from a point to a line is the perpendicular to that line. This is why from here to here is the distance. It's the shortest distance, but it's the distance. We didn't go this way because it's not perpendicular. It has to be perpendicular. So again, over here, from this point over to this line, has to be perpendicular to it. So we drew a perpendicular from here to here. So RP is equal to, according to the theorem, RM. So knowing that, and we've got expressions for both of these, we can use those expressions. Excuse me, this was not the perpendicular bisector theorem, this is the angle bisector theorem. And so using these two, these are congruent, we say 7x, or 7x is RM, and it's equal to RP, which is 2x plus 25. Solving for x, we subtract 2x from both sides. We get 25 equals 5x. Divide both sides by 5, and x is equal to 5. Therefore, the length of RP was 2x plus 25. Substituting in for x, 5, we get 2 times 5 plus 25. 2 times 10 is 20 plus 25 gives us 45. So RP, or the length of segment RP, is 45. Of course, MR will also be 45.